another Festival of Ideas 2024 here at the University of York. My name is Chris Stewart. I am a freelance science communicator, which basically means that I'll do almost literally anything for money, working with scientists like this one. This is Dr. Emily Brunsden.
Hello.
Who is an astronomer here at the University of York, an actual bona fide astronomer. She knows what she's talking about. Which is lucky because this is an astronomy podcast. And I'm not an astronomer, so it's really lucky one of us is. Now, this is all preamble. We haven't actually started yet. This isn't actually real. Because we always kick off our podcast. We've been going, the Syzygy podcast has been going since about 2018, which is ridiculous.
A long time.
Thank you. And we've done about 120 episodes now. Can I just show of hands, have you actually seen, or heard, rather, I've shown you before? We've got a smattering. I call that a smattering.
Yeah.
Family members don't count, by the way. It's nice that Emily's mum and dad are in the audience here today. Yeah. All the way from New Zealand. Give them a big round of applause. I know that my mum in Australia is listening to this, and mum is totally fine. That's fine. It's totally fine. No, it's not.
Next time.
She couldn't be here. She's actually fine and crying in Australia right now, so she couldn't. So what was my point? My point was that we normally start the show with our theme music. And the way it goes is this. We run the theme music, and someone comes and tapes things to our back. We run the theme music, I announce what the show is, and then at the end of the theme music in a live show, you lot go berserk, because remember we're in Wembley, right? This is huge, this is enormous. Just do a quick battery change. This is behind the scenes stuff here. Excellent, good. Hey, we're back. Can we hear you?
I don't know if you don't go skip.
There we are.
There we go.
Fantastic. I did think I was projecting a bit there. There we are. Yes, so, theme music. That's what I was saying. We do the theme music, I announce the show, and then at the end of the theme music, you guys go berserk in a sort of full-on Wembley style. So, can we just do that? Are you ready? Let's give it a try. Syzygy podcast recorded live at the 2024 Festival of Ideas. And then you Thank you for that utterly spontaneous round of applause. That didn't sound rehearsed at all. As I mentioned before, this is the Syzygy podcast. My name is Chris Stewart. This is Dr. Emily Brunsden, astronomer extraordinaire here at the University of York. And we have been doing the Syzygy Astronomy podcast for 120 episodes now. Over that time, we've talked basically about everything in the cosmos. I think we've covered everything, and so we can all just go home now. We've covered in extensive detail. I mean, black holes come up a lot.
Yeah, a lot of black holes.
Heck of a lot about black holes. The cosmic microwave background we talked about neutrinos, we talked about how the sun and stars work, we talked about supernovae.
About James Webb many times.
We talked about James Webb Space Telescope and lots of other space telescopes and non-space telescopes all over the world, telescopes here at the University of York over at Emily's Astro Campus, which is her little baby. It's very cool. But one of the things that we haven't talked about terribly much at all is that there's actually a lot of astronomy that you can check out for yourself just by going outside and looking at things.
Can I just say, Chris?
Yeah.
We are a podcast.
Yeah.
So the first word there could be one of the
reasons
why we haven't quite got around to
yes,
doing
all right. This has come up in 120 episodes. Podcast being an audio medium. And astronomy being a very visual subject does make it a little bit difficult. On the podcast, we do actually put a lot of pictures up, and those of you who use any kind of modern smart device can look down at your phone while you're listening and go, oh, there's pictures, fantastic. And we put in a lot of work to make an audio podcast very visual. I don't know why we started it as a podcast. We should have just jumped straight to YouTube. But we didn't, and here we are. But your point is well taken. it's very visual, and there are things that you people, and people in general in the world, can do to get outside and take a look at. And I thought we would look this time at a couple of things which have happened recently, and a couple of things which are coming up, which are quite visible to the naked eye. And the first thing I thought we'd start talking about is auroras. Aurorae, aurorae, aurorae. Any Latin people in the audience? Anyone speak Latin? How would you pronounce it? Well, that's true. That's one kind, but there is aurora australis, and there's two Antipodeans here. We'd like to challenge your definition there. Yes, aurora being singular, but aurorae. We're going to go with auroras tonight because there's no Latins here in the audience. Auroras. Now, quick show of hands. Who here on May 10th saw that? Just stick your hands up nice and high. Fantastic.
That's excellent.
And on a scale of 1 to good Lord, how amazing was it? Anyone in the front row? See how, it was good? It was pretty extraordinary, wasn't it? Yeah, once in a lifetime. Remember that. That's important. I mean, yes, up near the poles happens a lot. Emily, you've seen auroras?
I've seen aurora australis.
You've seen aurora australis, which is
even more exciting in this sort of space because it's actually a much more difficult aurora to see.
Why?
Well, partly because there's less land towards the South Pole, right? There's just less land, less people. It's also,
if you discount Antarctica itself, which is huge, but not many people.
Yeah, if you are lucky enough to go to Antarctica, it's obviously relatively easy. But if you are from anywhere else in the southern hemisphere, so South America, Australia, New Zealand, we're actually quite far north compared to how far
from the pole.
This is
You're
going to be
north
upside down.
from the pole.
Yes. We're relatively distant from the pole compared to where we are now. York, we're about 56 degrees north, where I do the majority of my in-person observing at the University of Canterbury's Mount John Observatory.
In New Zealand.
In New Zealand. It's 44 south. So that's...
Right. Yes.
We're already more north.
44 south is quite different to 50... What are we here? 56 north. Yes. What you're saying is Australia and New Zealand are a bloody long way away from the pole.
Yes. That's right.
Yeah. But this thing, May 10th this year, was one heck of a show. Right? These are just some of the photos that I've collected from around the interwebs. This is just from York. Right? There are so many photos that you can take. I do like this one over on the side here. It's nice to see that the cops were out doing their good work. They weren't so busy as to not stop and take a good picture of their police car with the aurora in the background. But yeah, just amazing. I'm not entirely convinced that the one of the Minster isn't photoshopped, but I'm prepared to take their word for it that is legit. It was absolutely extraordinary. And I thought we'd talk a little bit about what just happened? Why did that happen? Well, here it is. That is what happened. So Emily, talk us through this. What are we looking at?
The sun kind of happened.
The sun happened.
Which is a bit weird because it happened at night, right?
Well, actually. Yeah, talk us through that one.
So we have a sun, and our sun goes through a cyclical process where you have them. Actually, this is the crazy bit. So I'm going to go all the way back. I'm going all the way back here.
We're going
to come way back from this. The sun is really different to the Earth. The Earth's magnetic field behaves like a bar magnet. It's got a north pole, it's got a south pole, and we actually were just talking about that effectively, right? The sun kind of behaves like a bar magnet, but only when it wants to, effectively. And the sun has this amazing ability to not only only sometimes behave a bit like a bar magnet, but actually reverse, totally flip. So what is the North Pole at one point in the sun's cycle actually flips over and becomes the south magnetic pole.
That happens to the Earth as well from time to time, right?
Really
rarely.
Yeah.
Like tens of thousands, hundreds of thousands, millions of years?
Yeah.
People keep talking about it's going to happen to the Earth like it's any day now. It's like, well, yeah, plus or minus like 100,000 years. So don't hold your breath. But the sun's doing this how often?
Every 11 years, more or less.
Right.
And it's crazy because you're trying to think, you see these lovely pictures of the Earth, with its bar magnet, and it's got a north pole and a south pole. So it's all just very well behaved. It's like, it's perfect, like introductory science of
Nice.
magnets.
Easy.
That's how they work. They've got north and south. The sun is an utter mess. It is just horrible. And if I tried to show you a picture of the magnetic field of the sun, you'd be horrified, basically, because it is just twists and turns and spirals and all sorts of contorted shapes.
Bizarre, right? Because, I mean, the sun just feels like this constant thing in the sky, right? I mean, when you can see it, okay, I'm from Australia, we see the sun, but here you just have to take my word for it. Sometimes you can see the sun, right? And it feels so constant. It's this ball that it's the same. But when you look at it closely, not so much.
No, and it's actually a wonderful piece of physics, which is just saying that physics says when you've got charged particles that move, then there's a magnetic field that's associated with that. So moving charges, magnetic field. Turns out the surface of the sun, basically one giant sea of charged particles, and then the sun doesn't just have its surface moving kind of nice and well behaved and, rotating around in a really nice way. The sun, the poles rotate slower than the equator, so you get what we call differential rotation, you get messiness, you get swoops, you get swirls, you get this roiling kind of plasma on the surface. And all of that is charged particles. And so all of those charged particles have these magnetic fields associated with them. So the magnetic field pokes out of the surface of the sun, and it pokes back in, and it loops, and it curls, and it does all these amazing things. And what happens is the sun basically gets so twisted up and so contorted in all these magnetic fields that it gets to a point where it just completely flips, and it almost resets itself at that point. So this is an 11-year cycle, the full 22 years, because you go from north to south to north back again, so 22 years to do it twice. That's called a Hale cycle, the full 22 years. But we call this just 11-year block, let's say, of going really twisted and contorted. Just a solar cycle.
Just a cycle?
Yeah,
yep.
Just a cycle.
Okay, and where are we in the current solar cycle now?
So we are in solar cycle number 25. Now, the sun is very old. This is not the 25th solar cycle that's ever been. It's the 25th one since, I think, 1755.
Do you know, when I was looking at this the other day, stupid me, I thought it was solar cycle 25 because it's going to peak in 2025. Okay, well,
that's a happy coincidence.
We'll come back to that in a second. But just up here on the screen, and again, listeners at home, if you're not seeing the visuals of this one, please forgive us. Look, I'm prioritising the live audience here because they pay. You're paid, right? We're getting money for this. On the left here, we can see a very large green blob which has got a very large red core to it. And this is from the NOAA, which is the National Office of Atmospheric something, in America, the Space Weather Prediction Center. But these are their actual measurements of what happened on May the 10th. And on anyone's scale, that big red blob means something big has just happened. It's much, much larger than you would normally expect the aurora blob to be. Normally it's sort of a bit of a green band around the North Pole. This is just looking at the North Pole. It's an equivalent down in the south. But no, that was huge, and that's the reason why suddenly on May 10th everyone went nuts, going, look, the sky is on fire. This is crazy. And on the right, Emily, what's on the right?
That's our little friend 3664.
And 3664 is what?
3664 is a sunspot. So this is actually the, I guess, culprit.
This is the culprit. That's to blame for all the fun. Or to thank, I guess, really.
Yeah.
Responsible.
Yeah, so we'll come back to the cycles, but as we go through the cycles, when the sun gets really twisted and turned and the magnetic fields get all messed up, what starts to happen is you get bits of magnetic field that poke up through the surface and bits that poke down. And when the bits that poke down, they can drag hot surface material down, deep down into the sun. And so when we're looking at a sunspot, we're seeing one of these points where effectively the hot surface is being dragged down and being replaced by some cooler stuff. Now,
cooler.
Yeah.
This is the sun we're talking about here.
This is the sun.
So it's all relative.
So all the yellow is basically 6,000 degrees, right? Mm-hmm. And the very deepest black is only a few hundred degrees cooler than that.
Right, so still 5,500+ degrees.
Yeah.
Hot,
So
but cooler.
It's hot but cooler than its surroundings, so it looks like it's a dark splodge.
But why do we say that that's responsible? Like, what happened there?
Well, that little spot then, some of those magnetic field lines actually twisted and broke. And when they broke, they sent out all these charged particles straight out into space. And we happened to be in the flight path.
Yeah. And is that a coronal mass ejection? Is that what we're talking about?
I don't know if this one was quite at that level. So there's different scales of these eruptions. You can get sort of smaller ones and bigger ones. I don't think this one quite reached the full CME,
right?
Which is like the real, we've got to be really careful.
Which is like coronal, which is the corona of the sun, which is sort of the outer layer.
Sun,
mass stuff, ejection, flung off, right? And a big one of those, if it were to come in our direction, would that be good or bad?
That would be very bad.
That would be very bad.
Yeah,
so
very
as opposed to, hey look, the sky's purple, it would be, why doesn't anything work at all? Oh, it's because all the satellites have burned out and all communication on the planet is gone. So that didn't happen. But we can see, so this is an image from, again, NASA and the European Space Agency and SOHO, which is the Solar Observatory, something?
Yes, it's a series of solar observatories, yeah.
The ring in the middle here, I'm presuming, is blocking out the sun because it would be really, really bright.
Yeah, the sun's too bright to look at, even with the telescope.
But this is, you can see, 8th, 9th, the 5th, and then suddenly we start getting quite considerable stuff being thrown off. And of course it takes a while for this stuff to actually reach us. But there were quite sizable amounts of stuff being flung off the sun, some of which...
And this is real stuff, right? So we know that light travels very, very quickly. So the light from the sun travels to us in more or less 8 minutes, right? This is stuff, this is ejections, this is charged particles. And charged particles, therefore, actually take time to reach us, typically a day or two.
Hence, stuff being flung off on the 9th and causing lots of fun on the 10th. And here is another more close-up image of that sunspot area. It's sort of flipped, but that's terrifying when you consider, Emily, how big is the Earth on that scale?
It's about that.
So that's the Earth. And that's why we had the aurora on the 10th. That's terrifying. If you've never gone and checked out some of the incredible just imagery that NASA and ESA and the other observing organizations around the world have of the sun, it will blow your mind what this thing does every day.
This is amazing. You can see a lot of this. You can actually see magnetic fields. Obviously, magnetic fields are normally invisible, right? You can't actually see them. But you can often see them on the surface of the sun because there are little charged particles following them. So these little loops that you're seeing, that eventually one of those loops sort of gets too big and breaks, and that's what's causing the ejection. But all those little lines and feathery loops that you can see, those are real magnetic field lines that you're watching bits of the sun, bits of the plasma soupiness of the surface of the sun come up off the surface, follow that loop and go down. It's awesome. You can see just physics in action.
Yeah. And the flip side to that is the equivalent happens here on Earth, doesn't it? The aurora comes from sort of the reverse of that. So take us through, why the colour? Why did that end up with, good Lord, look at the sky?
Yeah, so amazing. So these charged particles, they actually have a lot of energy, right? They've come from the surface of the sun, which is really hot and really charged. So lots of these charged particles come to the Earth. Now, I think, just as an aside, this happens all the time, but it was just that this happened in a much bigger blob of charged particles, right? We're basically, solar physicists like Lucy Green will tell us that we live inside the atmosphere of the sun, right? The sun is continually putting out this kind of wind of charged particles, and it's this background level of just normality for us, right? And the Earth's magnetic field protects us from it, from the harmful charged
without the magnetic field, we'd be a bit stuffed.
Oh, yeah. We'd be Mars, basically, which is not the way we want to go.
Yeah, and for anyone who's I'll get on Elon's rocket and head to Mars, you might just want to think that one through. Go through the risk assessment of that one. Because Mars is not a particularly hospitable environment, because it doesn't have the magnetic field.
No.
Right?
That's right.
To protect it from the sun's atmosphere. But we do.
That's right.
Okay.
Yeah. So our magnetic field is really important. It holds on to our atmosphere and it protects us from these kinds of just general charged particles raining down from the sun. But so when we do get a burst like this, what happens is those charged particles, they've come off the sun, they're merrily travelling through space. I think in this case we actually caught up with the blob. So it wasn't kind of like blob straight towards us, it was blob right in front of us and the Earth caught up to it.
We sort of moseyed into it.
Yeah, that's right. And so we picked them up as they went along the way, and charged particles, magnetic field. Charged particles interact with Earth's magnetic field just like they were interacting with the sun's magnetic field. And so that's why they sort of get shuffled towards the poles, the magnetic poles of the Earth. So they get caught up in the Earth's magnetic field lines and they start spiralling around them, heading towards the north and south magnetic poles.
Yeah, because the magnetic fields of the Earth, it's like a big bar magnet. If you remember back to school, bar magnets have loops of magnetic field that come out of one end, loop around and go in at the other end. And the Earth is like that. And so there's magnetic field concentrated around the poles. And the geometry of that means that charged particles spiral their way towards where it's most concentrated, which is around the North Pole, aurora borealis, and the South Pole, which is aurora australis. But why the colour?
Right, yeah, now this is where it gets cool. So these charged particles, they're very energetic and they start whacking into the molecules of our atmosphere around the poles. So our atmosphere, Earth's atmosphere, is nitrogen, oxygen, and a little bit of other stuff, right? Mostly nitrogen and oxygen. And in fact, it's mostly the oxygen that's interestingly causing these aurora. Because if you're smashed into by a charged particle as an oxygen molecule, you suddenly find you've got a lot more energy than you normally would have, right? So that energy from that charged particle is transferred to the oxygen molecule. The oxygen molecule actually moves into a higher energy state, so it's got this extra bit of energy, but it can't do anything with it, and so it needs to get rid of it, basically. And so to transition, to get rid of that energy, it will emit a photon. And the photons that oxygen emits mostly are in the green.
Right, so hence the green colour normally associated with aurora. Yeah.
So charged particles are coming in, exciting all these oxygen molecules, and then to get back to normality, they're just giving off these green photons, green light. And then what's quite exciting is then when you get really energetic stuff, so really bright aurorae, then the very high atmosphere oxygen molecules actually emit red light. So you get this banded structure, which you may have picked up in many of those photos, where the green is kind of the lower atmosphere and the red is in the top. And you only get the red when it's really good.
When it's really going off, is when you get the red ones. Yeah. And then purple presumably is a
nitrogen,
mix of
there's a bit of nitrogen and stuff like that, yeah. So other colours are rarer, but broadly.
Yeah. So when you see the really colourful displays, like we got, that's a sign that things are really going off.
Oh, yeah.
So that's awesome. We were talking about cycle 25. Don't worry, we don't have terribly many graphs of data, but this is cycle 25, which I thought, as I said, was because 2024, 2026, 2025 is in the middle there. Like it's 25. Well, wait, no, it's not. That's just coincidence.
No, it is just coincidence.
I learned something.
That one. So what we're plotting on this graph is on the bottom axis here is time. So we're looking at years. So we're coming from 2020, just a few years ago, and we're looking at what is predicted to happen over the sunspot cycle for the next few years. On the top axis, on the y-axis, what we're plotting is the number of sunspots that we can see on the sun. And this is a type of plot that's been done for literally hundreds of years, because if you're patient enough and you live in a sunny enough place, you can go out there every day and count the number of sunspots that are on the surface of the sun.
To be clear, you're not doing that by looking at the sun and going 1, 2. Don't do that.
Well, they did do that, but it's not a good idea.
You can't look at the sun. You have to use special equipment to look at the sun.
Yeah.
But you can't just count them.
Yeah. So that's why 1755, basically, that's when we got telescopes and we started doing projections of the sun onto a screen and started counting. And
so that's cycle 1.
Yeah.
And now we're up to cycle 25. Every 11 years or every 22 years?
Roughly 11 years for each cycle.
Right. But the important bit is that graph has gone up at this point, right? down here in 2020, things were very quiet. Not a lot going on the sun. Pretty quiet. Just hanging out. Still being the sun, giving us warmth, giving us all that light. It's great. No problem. Nothing to be worried about. But its activity is increasing. And the red line there is the predicted, what we think, we, being the astronomical community of which I consider myself a part. And then the black is what's actually happening. And so we seem to be beating predictions here. This is a
really
bigger than we
interesting.
expected.
Yeah, so the last 3 cycles, so the last few decades actually, have been fairly quiet cycles. The peaks haven't been very high. And that bottom squiggly line, you can see that's kind of the zoomed out version of this. So you can see all the way back to actually, I think that's the first cycle at the very end.
Could be, yeah.
And so you can see actually sort of in the 1940s, 1950s, actually the sun was much more active. So we had a lot of exciting stuff going on. But over the last few decades, it's been pretty quiet. And all predictions were saying that, well, the last cycle was really quiet, which was actually really annoying because it was running a lot of teaching where students have to count the sunspots on the surface of the sun. That's a really hard thing to do when there's no sunspots.
I'm sure it wasn't personal, Emily, but I can understand the frustration. Yes.
Yeah.
And you can see that, second from the end there. And it was sort of, it's going up on this now, can't be bothered.
Yeah.
Can't be asked. But here we are, we're beating predictions this time around, and so far so good. And predictions are that 2024, maybe 2025, really good year for auroras, right?
Yeah, so what we thought was basically we're going to see something quite quiet again, but that blue line, which is the average basically, is saying that not only are we getting more activity sooner, but it looks like we're going to be at a much higher peak than we thought we were going to be.
Fingers crossed.
And this is good. I mean, this is a nice level of activity. It's a level of we're going to get nice sunspots to look at, we're going to get nice aurora, we're going to get a few sort of ejections that are pretty nice, but it's not the kind of, whoa, we need to be really worried about this.
It's not dig a bunker level.
Yeah, we need to start evacuating astronauts off the International Space Station.
Oh, God, I wasn't even thinking about that. But yeah, there's people up there who are not protected as we are down here in quite the same way. Yeah, you need to be careful.
So this is not kind of levels of concern, it's just levels of like really nice activity. Yeah. Like go out and look at aurora.
Yeah, cool. So that's good to know. So if you want to go and see an aurora, normally you'd be booking a ticket on one of these things. Emily, should these people now be going out and spending their hard-earned cash?
Well, probably not for a few months.
Right.
Because as you're probably aware, we're in summertime and there's very little darkness, especially the further you go north.
Yes, that is true. That is true. We are coming into the northern summer. Course.
Yeah.
And that means that the further north you go, the less darkness there is. And so the less chance you've got to actually see this stuff. So let's hope that we don't have any really big activity causing really great aurora that's basically invisible to us here in the northern hemisphere.
Yeah. Fun fact, York actually currently doesn't have a proper night.
What?
So the way that we define astronomical night, particularly, is we wait for it to see where the sun has to be more than 18 degrees below the horizon. Just doesn't happen.
Right, good.
The sun's just skipping below the horizon.
That could be
between about 11 and 4. And
that could explain why I've been sleeping so bad.
Anyway.
So that's part one, right? That's one thing that you can go out and see. Particularly like this year, next year, like
this
keep
winter,
your eyes and like as autumn and winter comes, as we start getting proper night again. And one thing that you can do is actually go to your smartphone app store, if you have a smartphone and if you know how to use the app store, and download one of the several apps that will alert you if an aurora is likely. Because there are services around the world that put out, like, hey, stuff's going down on the sun, everyone get ready, in like 8 hours time, red alert, like get outside and see it.
Can
really
we just do one last thing? Can we just get back to some of those pictures from the York community?
Like that one?
Yeah, any of these. So anyone who looked at it, you looked at it with your eye alone, did you see that?
No, not the colours. You can see different, but not the colours.
Yeah, so I thought this would be useful to pick up on.
Worth picking up. I know a couple of people who swear that they really did see some different flashes of colour, and I think the more you are out in the darkness, away from the city lights, the more possible it is. But yeah, what's going on here?
Yeah, so actually our eyes are really rubbish at picking up low levels of colour and light. So we have rods and cones in our eyes, and I'm going to get this hopefully the right way around. I think it's the rods that pick up whether or not you can see light, and the cones tell you the colour. Now the rods.
Can anyone confirm or deny?
I think that's the way around.
Cone fans in the audience. Yeah. Let's assume you're right.
Okay, we'll go with
For the
that.
sake of an
If not, just reverse that.
Yeah.
So the rods are picking up whether, and they're very sensitive. You can see objects when it's quite dark, right? At the moment, if you get out of bed at 2 o'clock in the morning, you can probably see where your bed is and where the door is and whatever, right? If you just let your eyes adjust. But you'll be looking in effectively black and white. You won't be able to see colour. And that's because the cones are much less sensitive to, you need a lot of photons coming into your eyes to pick up colour. But to pick up shape and structure and grayscale, you need much less. So when you go and look at aurora, they are bright, but comparatively, right? So you'll be seeing things like these sheets of white and grey. That's the first thing that you really see. And you can see them moving. They do move as the particles move around. But I wouldn't want people to be so disappointed if you think that you're going to see quite like that. If it gets really bright, you can. I've seen green once in my experience. So if it gets really bright, you see a bit of green.
But that's why you take your phone, right?
Yes.
Because your phone will take a long exposure, and it's got much more sensitive pixels than we have, rods and cones.
Yeah.
And so you'll get fun stuff like that when you control different.
Exactly.
Yeah, very nice, very nice. Listen, that brings us to the end of part one. I thought we'd take a moment to see whether or not anyone has any questions about that stuff, or indeed anything else sort of sun related or anything along those lines. Do I have to do anything to turn this on, or? No. Testing, 1, 2. Anyone got any questions? Over here, on the side.
How would strange matter affect the sun if it hit it?
How would strange matter affect the sun if we... Okay. Whoa, let's just rewind. Strange matter, you're talking quarks, right? Okay, so let's rewind. I am not an astronomer, but I used to be a particle physicist, so I'll give this one a go, right? Atoms. Stop me when we reach unfamiliar territory. Atoms. We're happy? Atoms. Come across atoms before. Nucleus of the atom. A little bit in the middle, yeah? Nuclear physics. We've heard of that. Protons and neutrons. Inside there, yeah? It's a lot of nodding going on. Quarks. Inside the protons and neutrons, there are quarks that are called up quarks and down quarks. Let's not get too hung up on that. But there are other kinds of quarks, aren't there? Can you name them all? There are 6. Up, down, what was the one you just said? Strange. Do you know any others?
No.
Okay, the others. The names get weirder, right? Up, down, and they discovered a third one, so that was strange. And then they discovered another one, so we've already done strange. So charm, we'll go with charm. And then they found 2 more, and initially they were called truth and beauty. And to me, they are still truth and beauty. But then the Americans went, no, that's just too cute. We're going to call it top and bottom. Fine. So strange matter is in some ways hypothetical. We can produce it in particle accelerators like in CERN, but it only lasts for a fraction of a second. But there is a possibility that some forms of strange quark matter could last much longer. And if it does, there is also very, very, very small chance that if it encounters some other matter, it turns that into strange matter as well through a special interaction. And then that snowballs. And so there's a really, really tiny chance that if some strange matter were created and, for example, ran into the sun, that at roughly the speed of light, the sun would turn into a huge ball of strange matter, and we'd all die? I guess.
You could have just led with that, Chris.
Yeah. There we are, Quarks 101. Anyone else got a question? Yes, right up the back.
So, the graph of the sunspot numbers appeared to be modulated over maybe a 100-year period. Is that just coincidental, or is there another process over the top?
So you're saying that graph, which goes up and down and up and down and up and down, but did seem to have, if you're looking along the bottom here, does seem to have another cycle over a longer period of time. It seems to be up sort of between 1800 and 1900, and between 1900 and 2000. There seems to be peaks and lows. Emily,
yes.
Is there another much longer cycle?
Well, we don't know for sure because we don't have enough data. But
right, we've only got 1, maybe 3 data.
We do know that this bit here was weird. This is called the Maunder minimum. And this was a really strange time when the sun just kind of stopped being sunny. Well, at least not in terms of our daylight, but in terms of having spots and so on. We don't know what caused that, but it did have some knock-on effects to obviously the amount of charged particles and aurora and things like that came through. There is also another one, I think it might be this one actually, that's called the modern minimum.
Yeah. Weird. What
That
happened?
one has a name, I think, as well. But yeah, we just don't have enough data to say truly if there is something going on.
And it's going to take a while before we get enough data. 2 data points can draw a straight line. 3 data points, is it a straight line? We don't know. We've got 3 currently, so let's just keep going. Talk to us in several hundred years, I think. We should move on to part 2, which is another thing that you can see really quite readily out there in the world, which is astronomy related, and actually also turns out sun related, which is eclipses. Right? And there was one heck of an eclipse this year. Not for us.
No.
We didn't get to see it, but the Americans did.
Yeah.
When was this, Emily?
This was April, I think it was April the 8th, was it? Early April.
Yes.
Earlier this year. And we had this wonderful, it was wonderful Syzygy.
About episode 3, a friend of ours gave us a Syzygy bell because it became clear that, the name of the podcast is Syzygy, and it means an alignment of 3 celestial bodies, like an eclipse. We were probably going to talk about that a bit, and so every time Syzygy comes up, we have to hit the Syzygy bell, which is actually rarer than we thought. So that's been sitting gathering dust, but we're really glad we got to use it tonight.
Exactly, yeah. So Syzygy, it means that we've got the moon passed in between the Earth and the Sun. Now, and you'd think naively that actually that should happen all the time. The moon goes around the Earth.
Yep.
The moon takes about a month to go round. So therefore, every month we should have a wonderful eclipse where the moon blocks the light from the sun. It's a bit more complicated.
It doesn't work that way. It turns out space is 3D and it's complicated.
Yeah, and actually the moon's orbit's not 100% circular. So sometimes when it's in between us and the sun, it's actually a little bit further away, and that means that it doesn't quite block all the sun. Because this and all the things that we're going to be talking about to do with the solar eclipse, this is one of the times when this is just a weird coincidence. They don't happen all the time in science, but it is a weird coincidence that we live, and a great coincidence, that we live in a time when the moon in the sky is exactly the same size as the sun.
When you say exactly.
Like, really, pretty much.
Really close.
Exactly.
And what are the odds?
Yeah.
Seriously, what are the odds? It almost makes you believe.
You cook up any set of planet and moon system. The moon, it could be any size, it could be any distance from its planet. In fact, the moon is moving away from the Earth very, very slowly, but enough so that in a few hundred years' time, we're not going to see any more of these eclipses because the moon will be too small in the sky to block.
Does that mean hundreds of years ago eclipses were bigger? They lasted longer? Because the moon was a bit closer?
A little bit longer, but not super. They would happen slightly more frequently, but yeah, so we're just lucky. It's weird. It's just the weirdest.
What are the odds of that happening at exactly the time in human evolutionary and sort of knowledge development for us to be able to recognise that? That's just wild, right? It's just insane. But hey, coincidence, right? With lots of things happening all the time, sometimes weird stuff.
Sometimes you get really lucky. Yeah.
This picture is obviously not from down here. This is taken from the International Space Station, and that is the shadow of the eclipse. That's what an eclipse looks like if you're not down here, if you're up there. I know, here, that's terrifying. It almost looks like end of the world stuff, but no, it's just a shadow of the moon. And actually, in a weird way, it's kind of surprising it's that small. But you need to remember the moon is not terribly big, and it's actually a really long way away. And the sun's a really long way away. So that's what it looks like. That's kind of cool. So the eclipse was only this year, a full total eclipse from America. We'll show you the path of the eclipse in a second. Hands up in the room. Has anyone ever been present for a full, proper, actual, bona fide solar eclipse, the full thing? Okay. For those of you who haven't, you may be thinking, what's the big deal? And this is time-lapse footage of taken for this eclipse in America. And like you can see the light coming and going from clouds, you think it was probably like that, right? But no, it's something significantly more impressive than that. Because as the moon moves in front of the sun, it goes proper black, right? It really is like, that just happened. It's extraordinary. And it is one of those things which is worth travelling to go and find. It really, really is. You've seen a full eclipse?
Saw a total solar eclipse in November 2012 in Cairns.
In Cairns in Australia?
Yeah, that country I sometimes acknowledge.
Yeah, I was in Australia in 2012. Didn't see it. Cairns is a long way, right? I lived in Sydney, which is down here. And Cairns is up there. And on UK scales, you go, well, that's probably half a day's drive. That's 4,000 kilometres away. That's a really long way. So no, I didn't go to see that one, unfortunately. Plus I had small children, so blame the kids. So yeah, definitely worth going to see. This is the path, and if you are interested in knowing more about these sorts of things and finding out when they're going to happen, I cannot recommend more timeanddate.com, which gives you everything from what's the time, and what's the time in this place, and what's the time on this date, but everything including astronomical stuff and eclipses and so on. It's an awesome website, so go check it out. And this was that eclipse, right? Started down in the Pacific somewhere, went across Mexico. This one was basically for the American audience, right? They set this one up for the USA. And so they got a really good look at it. But Emily, we didn't see it here.
No, we didn't. No.
We didn't get to see it here. So, before actually, we'll get on to other eclipses. We're going to get on to in a minute what our opportunities are for seeing eclipses for ourselves next. But what I wanted to talk about next was, like, okay, it's a syzygy, we get to ring the bell, that's fun. But an eclipse is also, from an astronomical point of view, kind of like, and, three things lined up. And, astronomically, is that useful, important, entertaining, valuable? What do we get out of eclipses, Emily?
Well, we obviously can do a lot of measurements of the sun, and actually, including this eclipse, there were a lot of people out there looking at the extended regions of the sun, because if you cast your mind back to that photo where we saw the big explosion of the sunspot, and there was there was that big black blob in the centre blocking out the sun.
Block out the really bright bits so that you can see the bits that are less bright.
Exactly. Yeah, when you got the moon to do that for you, I mean.
Bingo. Yep.
Yeah, easy.
Okay.
But of course we can learn a lot about also what's happening when we have a type of eclipse, really. It's definitely a syzygy.
Yep. Ping.
Yeah. Around other stars, when they have their planets actually travel in between their host star and us. So we've got a syzygy where it's Earth, star, and the planet actually comes in between us.
So this is an eclipse, but not for us. Or, it is for us, but it's not an eclipse with our moon and our sun. It's an eclipse for an exoplanet. Exoplanets are awesome. We've talked a lot about exoplanets on this podcast over the last 120 episodes. So just very quickly, Emily, exoplanets, what are they and why do we care?
Exoplanets, planets going around other stars, and because we're trying to find out if we're alone in the universe.
Nice summation. I would have probably taken about 6 minutes to do that, but no, in 10 seconds. Planets around other stars?
Yes. Yeah, so just like our solar system has 8 planets are going around it. There are, of course, other stars, and until very recently we had no idea if other stars had planets. We could derive theories and think, well, probably other planets are just a byproduct. When you form a star, you form kind of a set of planets with it.
If we've got 8, it seems unlikely that would be unique in the universe. But we didn't know, right? And now we do.
Yeah, so since 1995, we have actually been measuring and detecting these planets that are going around other stars in our galaxy and in some cases beyond. And the most successful detection method we have, or at least the method that has given us the most number of planets going around other stars, I think it's running at around sort of a few thousand now. Bona fide planets is this technique where we just look at a bunch of stars and just wait to see if a planet will travel in between us and that star.
So we'll take a good look at that in a second, but I did want to highlight a little while ago when NASA was wanting to promote its exoplanet research in a big way, someone in their marketing department came up with the genius idea of let's make old-style travel posters. And you can go to NASA's website and download these. They're quite fabulous. They look like the old, train travel posters. Go to, and they're just so much fun. Do you know anything about any of these?
Yeah, actually I do. So TRAPPIST is actually one of the, you're going to
That's
hear a
the
lot
one
about
on the
it.
right.
That's the last one. You're going to hear a lot about TRAPPIST in the next few years, because that is James Webb's basically, what are we going to call it? I don't know, the most famous set of planets that James Webb is going to be looking at to see if there's life on these planets.
James Webb being the James Webb Space Telescope,
Yeah.
which is like, Hubble. Everyone's heard of Hubble, I hope, which has been up there for ages. James Webb just blows all hell of water. It is incredible!
Yeah.
And it took a really long time to launch, and launched on Christmas Day back in 2022.
Yes.
Something like that. And it's working awesome. And so it's going to be having a look at that system, which has got like a whole bunch of planets.
6, I think.
6 planets.
6 planets there, and all of them have a possibility of perhaps having liquid water, depending on exactly what the maths turns out to be.
And you know what liquid water on an exoplanet means? It 100% means life.
Yeah.
No? Okay.
It's a good shot.
It's a start, right?
Yeah.
You never know. You never know. So go check out these posters. They're awesome. But the way that we find them, that Emily was talking about, is through this transit method. So here's a little animation that kind of shows that. Talk us through it.
Yeah, so we've got a planet that just happens to be in a nice alignment, so it travels in between us and its star. This little planet's just merrily going on its orbit, right? It has no idea that we're watching it. A little bit spooky. But we're looking at the star, and we don't see this blob, this wonderful animation that is the main picture here, right? All we see when we look at a star is what is actually in the background is that tiny pinprick of light, right? Even the closest stars we can't see in this kind of detail. They're just too far away. So instead what we look at is we look at one of those pinpricks and we wait for it to get a little bit dimmer, because that planet has come in between us and the star and blocked some of the light, just like the moon's blocking the light from the sun during an eclipse.
So that's what we see in this graph, right?
Yeah.
You can see it's bright, it's bright, it's bright, it's bright, it's bright, it's bright, gets a little bit dimmer, a little bit dimmer, a little bit dimmer, and bright again. How do you explain that? Well, something just got in the way. We didn't see what it was, but you can get a lot of information from that.
Yeah. Now, astronomy is one of the oldest sciences, and actually stellar astronomy is one of the oldest parts of astronomy, right? We've been looking at the stars for thousands upon thousands of years. So why is it we only figured this out in 1995? That drop is less than 1% of the light of that star that's dropped.
So that looks really impressive. Right? It's right down. It's like, where'd the star go? No, it's not that. It's like 1%.
Yeah.
And that's not something
At
you're going to
best.
see with like your naked eyes or
No.
binoculars or a small telescope.
No, so this really did require the next generation of space telescopes to really get deep down into the brightness, to be able to measure that 1% change.
Hence, since only the 1990s. Right? Yeah. Very cool. So listen, eclipses. If we want to see an eclipse, back to Earth.
Yeah.
If we want to see an eclipse, when's the next good York eclipse? Because we're local. We want to know. We want to know when we can go and see an eclipse.
Yeah, we had a couple, was about 2 or 3 years ago, we had a nice partial solar eclipse.
Yep.
Did anyone happen to catch that one in York? And it was sunny. And it was 11 o'clock in the daytime. It was really rather nice.
I mean, when you say a few years ago, like I think it was like 2017, like that's a while ago.
Okay.
But
Yeah.
living memory. For
Yeah,
at least
we've
some of us.
had 2, I think, since I've been in York, in the last 10 years.
Yep.
So they were partial, so they just sort of covered, the moon covered part of the sun, basically. It looked a little bit like Pac-Man gone a bit wrong, but you had a big chunk of the sun taken out. So you didn't see all this darkness. In fact, it wasn't even noticeably particularly dimmer, the sunlight. But when you look through a solar telescope or through a special filter where you protect your eyes, you could definitely see that there was something going on.
Yeah, I mean, it makes an enormous difference. And those of you who have actually seen it in person, the total eclipse compared to a partial eclipse is like literally night and day.
Oh,
Right?
yeah.
It's extraordinary. But this is still cool.
Yeah,
and it's
very
definitely
cool.
worth checking out.
Yeah, so this is, the next one we've got is coming up in the end of March. I think it's the 25th of March 2025. So it's not too long to have to wait, really.
It's less than a year.
March,
Yeah.
maybe.
And it'll look a bit like this, right? And again, from that fabulous website, time and date. Right, the moon will come across and take a big chunk out of the sun, and it reaches maximum about there. Won't pause, this is just for dramatic effect on the website. and then continue on its merry way. So, you'll be able to see it. Don't look with your naked eye, that's just wrong. Don't do that, but rather make yourself a special device, get some good viewing goggles, that kind of thing. But it'll be cool, right?
Yeah, definitely. So this is the type of event that we do, open up the Astro Campus obviously for special events like this. We've got a suite of solar telescopes that are safe to view the sun.
Yeah, so March next year, right? Keep your eyes open for it. The one that I'm really excited about is this one, being Australian. Because in 2028, this is going to happen. And, the one that the Americans ordered, the Australians ordered this one. And I got really excited about this one because, see where that dot is there? That's Sydney. That's where I'm from. And then I thought, well, I wonder, like, does it go close to Sydney? Or does it actually go across Sydney? It turns out it goes right across Sydney. But I looked at that a little bit harder and I thought, but the blob there is pointing like slightly above the line. And I used to live slightly south of the city. I wonder where it actually goes. That's my old house, right there, which I sold to move here. I don't own that anymore. I'm really annoyed now. Like, why couldn't that have been like 10 years ago? I could have just gone out and gone, it's right there. Like, it doesn't make any difference, I know, but that's awesome. What are the odds? That's so cool. Anyway, 2028.
Can I just make a point?
Airbnb prices in the city are going to be through the roof.
Oh, yeah.
I'm nervous at that time.
Can we just go back onto that zoom out? Because I'd just like to make a point that I think is missed a lot.
Which one?
The fact that New Zealand's also there.
Yeah, all right. It's exciting. Yes, New Zealand.
Yes.
And do you know where in New Zealand?
Yeah,
Like Dunedin or something?
This is actually my favourite wine region in New Zealand. This is called Central Otago. If you like a good Pinot Noir.
Yeah. Well, actually, because it's also going through above there. There's really good wineries in the valleys north of Sydney. So wine and eclipses. What could possibly go wrong? Yeah, so that's fun. But they're not the only kinds of eclipses because there's a different kind of eclipse.
Yeah, so you might have heard of lunar eclipses because these seem to come up, well, they do come up more often. So a lunar eclipse is a Syzygy. It's just the other way round. So this time it's the Earth's shadow on the moon. Now the Earth is a lot bigger than the moon, so the Earth has a much bigger shadow to cast in the moon's general direction. And so the moon does travel into the Earth's shadow more frequently than, of course, it blocks, So we get lunar eclipses much more frequently than we do get solar eclipses. And they're viewable from huge parts of the world. So instead of having these tiny little thin tracks across a map, which are where you can see the total solar eclipses, lunar eclipses, half the world can see them at a time.
Yeah, we sort of zoomed out a little bit here, but there's a hell of a lot of lunar eclipse going on right across Europe and Asia and so on. And we're sort of catching the edge of it.
Yeah, so our next one, we're actually in a little bit of a lull. We had quite a few about 3 years ago. We had about 2 or 3 in a single year that we were able to see from York, and I actually saw 2 of them, I think.
And it's not quite as mind-blowing as a total solar eclipse because you get that incredible difference between day and night. But it is still kind of cool. Hands up if you've seen a lunar eclipse here in the room. There's only a few people. The rest of you, you've got to check this out. It's really cool. Here's what we will see here in York. Now, you'll notice the screen's blank. That's because it's dark, right? This is just before the moon actually comes up. And so we'll see that happen very quickly. There. And when the moon comes up, it'll actually be in the middle of the eclipse, which is why it's dark and red. And it is. It's red. Like, it's wild. And then we will see it, just after it rises, come out of the eclipse, which will be kind of fun. And when is that?
September next year, September 25. Yeah.
So that's something very cool to look forward to as well. So go to timeanddate.com and just get a list of all of the eclipses that are coming up. Make your plans, start booking your travel and your accommodation now.
Yeah.
Right? Winery regions, New Zealand and Australia. Mention our names, we get a cut. So that's what's coming up. Now, we did kind of leave a little bit of time at the end for etc. because we didn't know how quickly we were going to go through all that and whether or not we were going to go overtime or undertime or what. And I think we probably pretty much used up our allotted time. So for the etc., We were going to talk about a couple of other things, which maybe we'll get to in future episodes of the podcast. We were going to have a little bit of a chat about planets lining up in the sky, which are called...
Well, depending on how they work, conjunctions, alignments, parades, whatever.
Which again is a little bit of a sort of from an astronomer's point of view, and like it's things lining up. Okay, well done everyone. Comets, which are much more interesting, and so we might have to have a bit of a chat about comets.
That's a whole episode.
That's a whole episode. And then something which does happen much less regularly, but is still really, really cool, and it's still a Syzygy, thank you very much, is transits. That is a picture of the transit of, I want to say Mercury, from a few years ago. And historically, scientifically, incredibly interesting. So again, check out future episodes of this podcast to find out more about those things. But what I thought we'd do now is quickly do a little bit of Q&A. We'll formally close the show by saying thank you so much for coming. This is the first live show that we've done since 2020. I want to say.
Yeah.
Which is just way too long. We love doing this sort of thing, but for one reason and another, it hasn't really been popular, or it hasn't really been possible for a while. So we love doing this live. Thank you very much for coming up, particularly as most of you have never heard of this before. Do check out our show, because we really enjoy talking about all this stuff. Take a postcard with you, because it gives you all the details. We're going to finish up with a little bit of Q&A while I get ready, because I've written a song to go with the event tonight. So Emily, do you want to just go and do a little bit of Q&A? Just a couple of questions.
Yeah. Well, I'll say a few things while you do that first.
Well, I guess
and then we'll obviously have some space for questions as well. So I wanted to say that basically, maybe we just get excited about this because it's stuff that we're into, it's stuff that we gel with. What I think is useful is that you can go out and see these astronomical phenomena, right? And they look cool, and you can get awesome pictures, and you can have all the grams that you want, right, from these kinds of things. But what is, I think, the most amazing thing isn't even the pictures, isn't even the sight. It's the thought behind it. So when you get to sit down and think, hey, there's an aurora, what does that really mean? That means that we've got this amazing, active, exciting things going on our sun, this boring yellow blob that we barely see in York, right? That's actually doing a lot of really cool stuff, and we get to see the effects of that in a really nice, dramatic way. And eclipses are like that too, because even though you can go out on almost any night and see the moon at some point if it's clear, you don't really stop and think about, actually, this is the biggest scale in our solar system. This is the sun and the moon, and they're moving and they're orbiting, and we're in this cosmic dance of things going around each other. And when you do take that moment to just pause and think about it, I think you appreciate what you're seeing that whole much more.
It really is awesome in the actual true sense of the word, rather than the sort of bastardized version that we use now. It truly is awe.
It is. Our universe is amazing, and we're so lucky to be able to just have this window into it.
Thank you so much, everyone, for coming. Please give it up for Dr. Emily Brunsden. We are due to actually finish right now, but I have gone through all this trouble. If anyone needs to go, then feel free. But if I can just take your indulgence for a couple of minutes, I wrote a little song. And the reason I wrote a song is because I tend to do that sort of thing. And the songs that I write are stupid. And they tend to be one-offs because they're related to the thing that we're doing on the night, and so they're not useful later, which is even more stupid. I don't know why I do this, but I do. But it's so hot off the presses, I don't even remember the words, which is why I've got this down here in front of me. But the song that I wrote, well, I'll stop doing the introduction. This is called Every Conversation That I Had on May the 11th. Hey, did you stay awake last night? The sky seemed like it was on fire. The flames were purple and green, unlike anything I've seen. I curtain for some choir. The sky was bright with unearthly light as we watched in awe down by the river. It was right there, like you could touch it if you tried. The memory of it now just makes me shiver. It's so rare for the northern lights to venture so far south, and rarer still for Yorkshire skies to be so cold and clear. And even the glow from the city couldn't stop the show that night. Check out this photo, it looks like a painting. So hey, did you see that flash of orange? No firework could ever compete with this display. Now a flash of purple, these phantom colours take your breath away. Hey, haven't you got a phone app that sends you an alert when there's a chance that you might see it? Must have been going crazy all day yesterday. Yeah, it was. Yeah. And hey, haven't you got a podcast about this sort of thing? You must have seen this before. No? That's weird. I mean, you knew what was going on right outside your window, right? I mean, you saw this. You were there, right? This magic, this majesty, this miracle. No, I didn't see that. No, I didn't see that. No, I was tired. I ignored the app. I didn't think it would be visible through the bright city lights. I went to bed, and I know that's the joke, right? 'Cause I do this for a living. Any other day I'd be out there, you'd believe. But in my defense, I mean, here's Emily, she's an actual astronomer. She didn't see it either. It's simply statistical. Chance infinitesimal of a York aurora borealis. So yes, it's true, I possibly just slept right through my only chance to see an aurora in Yorkshire. An aurora in Yorkshire, who'd believe ya? So, yes, I'd love to see. Please do show me your 30 or so improbably beautiful aurora photo. Thank you very much. We are going to be here sticking around. If you want to come and chat about any of this or anything else astronomical, enjoy the rest of the festival. There's other stuff still going on. Thank you for coming out. It's been great fun. Good night.
Good night.